Yes, thanks. Hi again. So in this talk, I would like to introduce the way we think we should expose T10-DIF signature offload for storage purposes. So introduction, I start with the introduction. What is T10-DIF? So basically, it's all about integrity. So storage system typically are multi-layered. They have multi-disciplines in the sense of memory blocks, OS file system that are involved, remote storage adapters. They can be NICs or HCAs, HBAs, and the storage controller itself. It can be any of the local storage controllers like SATA, SAS, and NVMe. And any of those layers has their own integrity check, right? The memory uses parity checks, essentially. Storage controllers use CRCs. On the wire, NICs essentially use checksums. But none of them have an end-to-end protection, like from OS bugs, driver bugs, if there's any issue with the disk controllers or their firmware, some administration errors, or even data at risk and wearing of the data. So we see, not we, but the T10-DIF committee see a great need for integrity protection for the storage end-to-end. And the signature or the protection needs to come with the data. If it originates from memory, it has to be in the memory. If it originates from the storage, it has to be saved on the storage. So what they came up with, the DIF, the data integrity field, it is basically an 8-byte integrity field, signature field, that is added to any storage block. So if essentially we're using 512 bytes storage block, which is pretty common, we are adding 8 bytes and growing it to 520 bytes. So these 8 bytes are built from, as described here, there's the guard block. The guard block is basically the CRC. This is pretty well defined in the T10-DIF spec, how to calculate the CRC. These are the 2 bytes of the signature block. There's an extra 2 bytes for application tags, so any user can push his own tags there. And there's extra 4 bytes that are used to identify the block itself. So essentially, it is being used by the 4 last. It is taken from the 4 last bytes of the logical block address of the block. So in this diagram, I'm trying to show a typical use case. So we can see here, there's like a distributed storage fabric. The storage is here, and here we have 2 initiators. One initiator is using the DIF. We can see here the network data that is being passed for storage access. So we can see here that data is interleaved with the signature. In this case, it's maybe a legacy initiator. It's not using DIF at all. Both of them can access the same target. If the target is using DIF, it can, in this case, whenever it receives data, it can check the signature and understand if there's any integrity check. If in this case, it won't be doing any integrity check in the data that is being received from this initiator. But on the storage itself, it can keep the signature block and can always validate whenever it reads it. And for this guy, it can transmit over the wire with the signature. For this guy, it can transmit without. So it can be a heterogeneous system with or without the DIF. And a more focused example is, in this case, is the I/O read. So we can see here 4 examples. On the first one here on the upper left, we can see that on the memory, again, this is an I/O read. So the initiator on its own memory doesn't want to keep the diff, the guard block, and all of that. So whenever it initiates a CDB for the read, and essentially that ends up with the storage target doing an RDMA write of the data that is being read to the initiator. So in this case, we validate at this point when we read the data which is kept with the signature on the RDMA write, on the requester side of the RDMA write. And also on the responder side, we do a validate again, and then we strip the signature because in this use case, we don't want to keep the signature blocks on the memory. And on the network, we can see that signature is being passed. So end to end, we do check the signature. In this case, it's similar to this guy, but here we do not want, the administrator don't want to see signature on the network. So signature validation is being done towards the storage memory, the target memory, and not toward the network or the initiator. So whenever we send with an RDMA write, we read the data, we validate the signature, and then strip the signature and send the data as raw. On this case, we actually have end-to-end. So we validate on the target side. We send the signature interleaved over the network, and then we validate again on the initiator side, and also keep the signature in the initiator memory. And that's the last example where data is not kept with signature on the storage side, but still we can keep the data on the initiator side with a signature. So we simply add. We can't validate because we didn't receive any signature, but we can add. So this was the IO read. IO write is similar in only the opposite way. In IO write, basically whenever a target receives an IO write CDB, we perform an RDMA read the data, and write it to the storage. And again, I don't need to walk through all of the 4 examples, but again, we can have similar combinations where signature can be in memory, signature can be in the target side memory, and across the network. And we do the validation or strip accordingly. So going to verbs, as we can see in cases of distributed storage, it makes sense that also a type of offload will be introduced to the NICs as well, because now the NICs are involved in transmitting and receiving storage traffic. And as we know, performing such CRC calculations are heavy CPU operations. So the basics of the addition to verbs is having the signature as a property of the memory region. So basically, diff calculation is being done if the memory region is of a signature, has a signature attribute. So we will add a signature attribute to that memory region with its attributes. So we'll see in the next slide what is needed. A single, typically in the storage use case, single memory region and key describe a single IO transaction. So it fits well. So we can have signature property per transaction. Also, once we thought it through, we were thinking, should this signature operation be a special WUKI, a special opcode of a post-send, or a memory region property? And then we thought about RDMA. With RDMA, when you are the responder side and you are the passive side, basically you don't have any CPU involved. So there's no WUKI's consumption if you don't have immediate. So this operation goes directly into memory. So we need something that describes the memory, and it fits well within the MR characteristics. And again, this is per transaction. So a single QP can serve both I mean, the other approach was to have it as a property of a QP. And then again, we wanted a single QP to be able to support protected and non-protected transactions, which is also a valid use case for storage systems. So what is needed to basically describe a signature? Again, MR can be with or without diff, obviously, if you use the signature or not. Then the diff field, should it be on a separate buffer or interleaved with the data? And then we can obviously describe what would be the block size of the signature, and if we should use CRC, checksum. Typically, for wire, we would use CRC. For memory, sometimes it's easier for NICs to support checksum. This was, I forgot to mention that those characteristics needs to be different for memory domain signature and wire domain. So that's why we have here, as I mentioned, the signature description separately for the memory and the wire. So again, for the wire, also we can turn on and off diff. On the wire case, it must be interleaved, and typically on wire we would use CRC, but still block size and CRC checksum can be configured. So IO operation, if you are using an MR that is signature enabled, will always go through signature processing. Again, according to the SIG-MR attributes. It can be a remote or local access if you're doing loopbacks and you would like to do some memory-to-memory transaction, or even send data from one VM to another, or if you have like a multi-host configuration, if you're familiar with the term. And hardware will basically do the right operation. If it needs to calculate and add it, if it has to strip, if it has to build and pass it. So all of that is described in the signature attributes and the type of operation you are performing: wire, memory, send, receive. Now, how do we handle an error? In case signature check failed, what do we do? So we need to understand that signature error is not a transport error. Traffic can still pass through the medium, through the network medium, and can pass CRC, and everything can be fine. But still, the signature can fail because it was, as I mentioned, some hardware bug, some software bug, some OS bug that corrupted the data before even sending it. So that's the whole point of signature, that you can check it end to end. So data in terms of the transport passed well, but it didn't fail in the signature case. In our case, the QP would not change its state. QP state, basically, if CRC failed, QP would go to error and indicate an error. In our case, we cannot modify the QP state because transport, there was no transport error, traffic passed fine, and also same QP can serve multiple entities. So if certain entity failed on its signature, it's incorrect to fail to turn this QP that serves other entity that was okay or even didn't use signature. So signature error should be checked separately and should be inspected after the transaction had occurred, obviously, because only then we can inspect and understand that there was an error. Also, this is a data path operation. It must be lightweight. Shouldn't involve hardware access, because then we just shoot ourselves in the foot. Also, that's fine because storage application knows when a transaction ended, so it can initiate this lightweight check by itself. Going a bit deeper to the API, so we actually use the same notion as the non-contiguous memory as I described this morning. We've added the IBV set layout call. So in this case, we have the IBV set layout signature, Again, the set layout, if you remember, enables you to modify MR characteristics, IBV-MR. And in this case, we also modify IBV-MR characteristics. And in this case, these are signature characteristics. And also, as Jason mentioned, we are now changing the approach where we have a more tailor-made function per operation and not using like a single entry point and having lots of switch cases to handle each scenario. So in this case, we have the set layout, and for signature, we've added set layout signature. And we can see here that the input parameter is the MR object, obviously, and then we follow it with the signature attributes. And the data itself, we have two scatter-gather entries here, one for describing the actual data we are performing integrity check or adding a signature, and the other is where the scatter-gather that describes the memory area for holding, for keeping the signature. So in case the signature is interleaved with the data, obviously it is not needed. So in terms of the signature attributes, as I mentioned, for the set layout set signature verb, we've added the IBV signature attributes. The signature attributes are two. We have one for the signature memory domain and one for the wire domain. In terms of the signature domain, we currently support only T10-DIF type of signature. So that's why we have only here T10-DIF. And then in terms of the T10-DIF, those are the attributes we support. The guard, the block guard, the 2-byte guard area of the signature, if it should be CRC or checksum. The protection information interval. What would be the block size? As I said, typically it is 512. The block guard seed, that's the seed for calculating the CRC. The application tag, which is apps for grabs. Each application can use it as it wishes. There's the reference tag. As I mentioned, the reference tag is usually a way to describe the block and the block address and mostly the last 4 bytes of the LBA. And then we have masking what actually we want to validate on the signature. So we can say we want to validate all the 8 bits, all the 8 bytes of the signature. So we have 8 bits describing each byte. And we have even more granular mask for the application tag. So application tag can be masked per bit. So we can verify only specific bits on the application tag. Now, continuing with error handling or with the flow where we check if the signature passed or not. So as I said, it's a lightweight operation. So whenever a transaction completes, we need to verify if there was or wasn't a signature check in case we would like to perform one, and only then can conclude the transaction successfully or not. So we've added the IBV check MR status, so we can check the MR for signature errors. We can see here that we can get the fail status, and we have in the sig_err struct here very detailed description what failed, the type of error, if it was an error in the guard tag or the ref tag or the application tag, what was the expected signature, what was the actual signature, the signature error offset, which block actually failed the signature check, and the MR, the key that failed the check. Pretty straightforward. A very important issue we've seen with that design is that typical IO read operations or storage protocol that implements such IO read is essentially sending a read request to the target from the initiator, and then the target performs the RDMA writes, providing the requested read data to the initiator. And right after doing those RDMA write, asynchronously calling post send on the same QP for sending a good response to the initiator, telling him or notifying him that the transaction completed successfully. So in this design, we basically rely on QP semantics, where those work request element of the RDMA write and the send of the good response would be sequential. So in cases where RDMA write would fail, a transport failure, the QP will turn into error state and will not process this trailing work request element that performs the notification, the send notification to the initiator side, telling him the transaction completed successfully. So in the best case, where usually everything is okay, we enjoy a very nice and fast, low latency notification of the completion of the transaction, and do not need to wait for these guys to provide us, for this last RDMA write to provide us the completion. But in our case, some validation can fail along the way in case we read the data from the target memory with a signature and send it to the initiator, either with or without the signature. When we perform the check here, we may fail. And as I said, it's not a transport failure. So the QP will not change state and will continue and process this good response work request element wrongfully. Obviously, the trivial solution would be to perform some fencing here, wait for the last RDMA write completion, and only then follow with the good response. But it is a performance killer and IOPS a killer, so we want to have something better. And the resolution for that is basically whenever there is a signature error that is happening, the QP will automatically revert to send queue drain state. So in this state, the QP is halting from work queue elements processing and basically generates a QP affiliated error or notification event which tells the application your QP moved to a send queue drain state and stopped processing work request element. And for the application to handle such a case, we've added two verbs, the IBV get current work request ID and cancel work request ID. So in this case, we can basically, in SQD state, as I said, the QP stopped processing its send queue portion of work request element, but you can still, as defined in the spec, you can still have wookies there. You can continue posting wookies. They won't be processed. So in our case, we would like to pop the last work request element on that send queue that was not processed and basically eliminate it, cancel it, because that work request element described a good response. So essentially what the application would do, as soon as it gets the SQD async affiliated event on its QP, it would call the get current work request ID, cancel the current work request ID, post a new bad response work request element, and move the QP with modify QP state to RTS, ready to send. So the flow is pretty straightforward, as you have seen. So the summary here is that we can see and we identify the great need for data integrity check, and it's much better, obviously, to drop corrupted data than receive it. Once we are going to network storage systems, integrity check offload can be performed by NICs and HCAs. It seems like a natural fit to a memory context attributes, as I explained. And in terms of the status of this work, So for kernel verbs, these APIs are already upstream. For user verbs, we do have an RFC already posted on the RDMA mailing list, and this is a work in progress to complete the contribution. And we do have an older version of this API supported in our Oved package. Any questions?
Yes, I have a few about the semantics of it. So first of all, you talked about the ordering in case of RDMA write and moving to SQD, but that's just for RDMA write? Is that something that the user can control? What if he does it on RDMA read or on send operations?
Whenever there's a signature error check, we move to the QP to an SQD state.
So, but with RDMA read, when you validate it on the way back, what does it mean to move to SQD? You don't know at what point it will happen, right?
So the main issue here was for an IO read transaction, because on IO read transaction, you actually have this parallel issue. With IO read, with RDMA read, it means that you are doing IO write. And on that case, the target has full knowledge of what's happening if the completion.
Yeah, I understand. So are you going to move to SQD in that case or not? Because it seems like there's no need for that, right? I mean, where's the semantic?
Yes, but the semantics, we want to keep the same semantics. So the plan currently is whenever there is a signature error, we automatically move to SQD state. If you feel otherwise, then
all I'm saying is that if it's a read, you don't know at what point that SQD will happen, right? You don't know what happens on the SQ at that point.
Yeah, but we want to keep the same semantics, independent on the type of opcode that you do on that QP. Okay, if that signature failed on the current IO transaction memory region, then we move to SQD. Okay, I think it's much simpler to keep the same semantics all across.
No, I understand. I'll tell you where I think it gets a bit more complicated. If you have, let's say, a signature MR on the RQ, okay, that happens in storage in capsule data. In that point, you're getting something on the RQ and you're going to move the SQ to SQ drain, the QP to SQ drain?
I thought that you were asking about RDMA read.
I started with RDMA read. I said, now it gets more complicated because I said,
no,
we want to keep that semantics.
For the responder side, we won't be turning to SQD. That's semantics. That's for the requester side, we will move the SQ to SQD, but on the responder side, we wouldn't.
Okay, and what about the semantics of the SQ operations? I mean, you didn't talk here about how it's going to look on the network, right? If there is something on the network that contains DIF, does the DMA length contain it? It doesn't contain it if he knows if it's on the other side?
Hold on, so the question, just to see that I understand the question. So you're saying there is a signature interleaved on the network traffic,
yes,
right? Ingress into the device, and I do have on my responder side, the transaction is targeted on my responder side to MR that is with signature characteristics.
First of all, I didn't really understand. Do you expect, if there is data on the wire, how will it look on the wire?
It is well defined in the T10-DIF committee.
No, but I'm talking about the Rocky packet. I'm understanding where it will be in the data stream. But now you have an RDMA write of 1K, so we have 1K plus 16 bytes. The DMA length is going to be 1K plus 16 bytes?
8 bytes.
There are two blocks in 1K, but
yeah,
okay.
So we will have, right, if you have 2 blocks, you have 8 bytes for the one block and 8 bytes for the second block, and it will be interleaved for each block.
Yeah, I understand, but the DMA length on the RDMA extension header, it will include that, but when it will be placed...
It is included in the data block.
No, I understand, but at the beginning of an RDMA write, there's an RDMA extension header that tells how much data there's going to be.
Yes, it will be included.
Okay, and
it is encapsulated into the Rocky packet, so the Rocky protocol is unaware of that. So size must include the whole
But it's not really that it's unaware of it, right? On the other side, you might need to strip it, meaning I got an RDMA of 1K plus 16 and I'm placing 1K.
You should differentiate between transport and application offload. you are a bit mixing the two. In transport, in terms of Rocky, it's unaware. He's doing its CRC, its BTH, its analysis, whatever, on the transport level. That's one. After you pass the transport level, you reach the application offload level, and in that case, we do the signature. That is why signature error is not a transport error. That's another reason. Yeah, so just make sure you differentiate between the two.
No, that's fine, but that means that an error that happens on the, let's say it got 1K and it was supposed to strip at that and it didn't, that happened on the...
Why it didn't? What do you mean?
Because the MR that it was writing to didn't have signature MR.
Yeah, so you're saying on the responser side, I had an MR that signature was not enabled on it.
Yes,
so I received the whole Rocky packet with the data interleaved with the signature, and it is now placed in my memory because my MR did not include any signature semantics. Just a second.
Okay.
Did not include any signature semantics, so I didn't do any strip, validate, or add, obviously.
Yes, but if that MR only has a place for, let's say, 1K in that example, that's an error. That is a transport error, right?
No, it's not. Hold on. If you had an application that has a bug in it, because you designed your system that way, just a second, that you send a larger buffer than the receiving allocated buffer, then of course, this is a transport error. It's unrelated to signature.
It's kind of related, right? Because that side thought it.
No, it's not.
Signature.
It's not because this is an application case. You had an application. You built your system that way. You designed an MR that is not contained signature, and
that's an application bug that caused a transport error.
Correct.
Okay. No, you're saying it's not related to the signature.
No, I'm saying it just different between the two. Signature is offload is an application offload. If you designed your system that one side is doing the signature and sending it across the fabric, and the other side is unaware of the signature and receiving the data with the signature as is, of course, you have to build the buffers accordingly. You know the block size, you know the signature size, everything is packed.
Okay. And what about the fact that you're canceling the current work request ID? That's just the current one?
So for the signature, yeah, that's a good question. We did think maybe having a more flexible call to cancel work request element, maybe cancel if you like in SQD state for other reasons, not because of signature, because it can happen if you like want to change the SL and maybe priority of that QP. So there are cases where you'd like to move to SQD state, so it might be useful if you can cancel other work request element. So far for signature, we do not need that, but feel free to comment on the mailing list if you feel that such addition is needed. We can consider it.
Okay.
So we're testing it and like to use it. Cool. Recommendations on, we found a problem, I guess, with performance for transferring large blocks. And so is there...
Larger than 512?
Yeah, 4 megabyte. So 256K getting 8+ gigs a second on EDR drops to 700 meg for larger transfers. And so that's in 4.2. So is there, I mean, we filed it, yeah. So MOFET. So is there a more current release or we just
so 4.2 is our latest. Yeah. I can hook you up with our storage guys that can maybe recommend on their statistics or their benchmark what they've seen, where they've seen any performance hits on certain block sizes. This is something we need our guys that work on those benchmark involvement. And
also on the ISER driver, there's some changes we probably would like to control.
In terms of signature of ISER traffic, you're asking?
Well, from the kernel to the card, there's a, you can have the kernel generate a checksum, and we would like to flip that on and off. So our fiber channel drivers, we can do that. And so I think we may have a way that we did this kind of in the back door, but some more configuration is...
So again, you would like to have the signature being validated on the controller also?
So yeah, the kernel, as part of the request to send, can generate its own checksum that the card then checks before it does.
Yes.
And so that has overhead, and we like to turn that off. So, or have the flexibility to disable it. And so typically we do disable that check.
So you would like to disable that check?
Yes, that's correct. Yeah.
And we are talking about signature,
Not signature. Well,
other topic.
It's in the ICER driver, right? Because if it's end-to-end, it's done in kernel memory, so they consider a transfer over PCI to the card part of the transfer, and so we typically turn that off. So,
I see.
Yeah.
And this is something we've added at latest releases, or?
It's just the driver's pretty new, and so it doesn't have as many configuration options as we'd probably like to see.
Okay. I'll get back to you regarding the performance.
Just to understand, it's up to the application to use it correctly, right? So if if the application register this memory region and then it sends a write, it needs to send a write, a single write, right? From the start.
Whatever. I mean, whenever you use this MR with signature properties, with single write, with multiple writes, with send.
But if it will send it one half, and then it will not start from the start of this block, and will start from the middle, and then go back, right? It cannot do it, right?
Yeah.
You expect it to do it consecutive writes.
Yeah, like whenever we send the block size that you've defined, either from the start of the memory buffer that is described by this MR, or by the middle, anyhow, you define whenever the point where you want to start, and we count 512 bytes. If that's the block size, then perform signature and add the 8 bytes trailing to that.
Okay, because it must be in order, right? You assume that it sends the data in order, not out of order, right?
You mean on the fabric, or?
I mean that, I don't know, you have a 512 block, and the user does write of 256 bytes, and then the rest of the 256 bytes. But if it will do it the other way, it will not work, right?
If you perform an operation that is below the block size that you've defined.
Yes, if it does a write of 256.
No, it wouldn't. You have to send something in block granularity. And
you have to send it, the blocks needs to be written in ascending order, right? You cannot have gaps. You cannot you cannot send them out of order, the blocks, right? You must
why is that? When you say out of order, you mean sorry?
If you have block 0, then 1, then 2, and then 3, and the user first writes block 3, and then block 0, and then block 1, right? You will have a problem, probably.
So it depends. First, there's two things here. First is how you receive it, if you would like to do the ordering on the receive side. And the second thing is that you need to take into account that we increment the reference tag according to the sequence. So we will increment it in the way, just a second, in the sequence you've posted those operations. So if you did out of order, you need to understand that when on the receiving side.
Okay, so I mean, this is an example for things that need to be specified. When you add such feature, it needs to be clear.
Okay.
Otherwise, it's
yeah, I completely agree. Any recommendation? We always, when we post the RFC, we also post the man page that describes all the characteristics and the attributes explanation. So, of course, nothing is perfect, and if we can clarify things, that any input would be welcomed.
Okay.
Thank you.